In this lesson we're continuing with the topic of trigonometry C, and we're looking at the wave function. So we're already familiar with the idea that we can combine wave functions, that's namely sin x and cos x, and we can add these together to have another wave function which we can express in one of the following forms at the bottom of the screen here. Now, we have previously learned now how to use our addition formulae to create two equations involving cos alpha and sin alpha, and we have then been able to solve these simultaneous equations for both k and alpha. So today we're going to look at examples like the following, where you can see here that we're expressing a sum of trigonometric functions as one single trigonometric function, which has a change in amplitude and a phase shift as well. So example 1 asks us to write 5 cos x plus 12 sin x in the form k cos of x minus alpha, where k is greater than 0 and alpha lies between 0 and 360 degrees. So our solution then, we firstly want to look at our graph just to see what it is that we're trying to look for. So we can see here that our amplitude lies somewhere between 10 and 15, and we can see that there's been a phase shift as well. Okay, so basically that's what we're being asked to find, is the amplitude and what the phase shift is from the graph of cos x. So if we firstly look at k cos of x minus alpha, and we use our addition formula of cos of x minus alpha to expand that, and we will obtain k cos of x cos alpha plus k sin of x sin alpha. We can now equate our coefficients. So looking at cos x first, you can see the coefficient of cos x in the expression we've been given is 5. And in our expansion, the coefficient is k cos of alpha. So that means that k cos of alpha is equal to 5. If we now look at sin of x, we can see that the coefficient of sin x is 12, and in our expansion, the coefficient is k sin of alpha. That means that k sin of alpha is equal to 12. So we've now got our two simultaneous equations, which we should be able to solve. So firstly, solving for k, we're going to square each of the equations. That will give us k squared times sin squared of alpha is equal to 144, and k squared times cos squared of alpha is equal to 25. Now if we add these together, get k squared times sin squared of alpha plus k squared times cos squared of alpha is equal to 144 plus 25. On the left hand side you can see that we've got a common factor of k squared, and on the right hand side we can evaluate that sum. So that will give us k squared times sin squared of alpha plus cos squared of alpha is equal to 169, and we should remember that sin squared of alpha plus cos squared of alpha is equal to 1. So k here must be equal to 13. We now need to solve for alpha. So we can take our two simultaneous equations which we came up with. So k sin of alpha over k cos of alpha is equal to 12 over 5. Our k's here will simplify to 1. And remember, sin alpha over cos alpha is equal to tan alpha. So tan alpha is equal to 12/5 here. Now we need to know which quadrant the alpha will lie in, the angle. So we can employ our cast diagram for this, or you could look at the graphs. And you can see here that k sin of alpha was equal to 12, that was positive. So the answer for that would have come from the first and second quadrant. And k cos of alpha equal to 5, that's also positive, so those answers would have been the first and fourth quadrants. So we can see then that our answer for alpha will come from the first quadrant. So inverse tan of 12/5 is equal to 67.4 degrees. And we now have all of the information that we need to write 5 cos x plus 12 sin x in the form k cos of x minus alpha. So that is 13 cos of x minus 67.4. And you can see if I go straight to plotting the graph of 13 cos of x minus 67.4, that we get exactly the same graph. Now, we were asked to express it in this form, k cos of x minus alpha. We may have been asked to express it in the form k cos of x plus alpha, in which case we would have had a different phase angle here. So that would have given us 13 cos of x plus 292.6, again giving us the same graph. We could have been asked to express it in terms of k sine of x minus alpha, once again giving us a different phase angle, but again giving us the same graph. And finally, we could have had the form k sine of x plus alpha, and the phase angle this time was 22.6, and again you can see that it gives us the same graph there. So I'll just pop back to example 1 just now, and if you pause the video and copy that down before coming back for example 2. Welcome back folks, and we'll look at example 2 now. We want to write 5 cos x minus 3 sin x in the form k cos of x minus alpha, where k is greater than 0 and alpha lies between 0 and 2 pi. So our solution then, we'll just have a quick look at the graph of 5 cos x minus 3 sin x firstly, and it looks something like this. Okay, so you can see that yes, we could express that in terms of the cosine function, but there has been an amplitude change and there has been a phase shift as well. So we need to find out what that amplitude change and what that phase shift actually is. So using our addition formula then, we know that k cos of x minus alpha will be equal to k cos x cos alpha plus k sin x sin alpha. We then need to equate coefficients to come up with our simultaneous equations for k cos alpha and k sin alpha. So examining the coefficients of our cos x first, we will obtain k cos of alpha equals 5, and examining our coefficients of sin x, we will obtain k sin of alpha equals negative 3. We will next solve for k. So we need to square out each of our equations. So we get that k squared times sin squared of alpha is equal to 9, and k squared times cos squared of alpha is equal to 25. If we add these equations together, you can see on the left hand side we have a common factor of k squared, and we can evaluate the right hand side. So that will give us k squared multiplied by sin squared of alpha plus cos squared of alpha, and that's equal to 34. Remember that sin squared of alpha plus cos squared of alpha is equal to 1. So k squared is equal to 34, and k is equal to root 34. We can now look at solving for alpha. So we can take each of our equations that we've come up with in here, and we can say that k sin of alpha over k cos of alpha is equal to negative 3/5. Remember, your k's here will simplify to 1, and sin alpha over cos alpha is equal to tan alpha. Now we can see here that tan alpha is negative, so we would assume that our answer is either coming from the second or the fourth quadrant, but we want to check that using the cast diagram and using our values that we had for k sin of alpha and k cos of alpha. So k sin of alpha was equal to negative 3, so the answers for that would come from the third and fourth quadrants, and k cos of alpha was positive. Answers would come from the first and fourth quadrants. So you can see here that our answer for alpha is going to come from the fourth quadrant. So inverse tan of 3/5 is equal to 0.54. Remember, we're working in radians for this question. So 2 pi minus 0.54 gives us 5.74. So alpha is equal to 5.74. And we now have all of the information required to express 5 cos x minus 3 sin x in the form k cos of x minus alpha. So that will give us root 34 times cos of x minus 5.74. And again, if we just plot that graph, you can see that it gives us exactly the same graph as we had originally for 5 cos x minus 3 sin x. And once again, we can look at the other forms that we may have been asked to express our answer in. So we were given this form, and we got the same graph. What if we'd been given k cos of x plus alpha? And you can see there again we would have a different phase angle. But we have the same graph. If we'd been asked to express it in the form k of sine of x minus alpha, we would have had root 34 still, but sine of x minus 4.17, again a different phase angle. And if we had been asked to express it in the form k of sine of x plus alpha, you can see once again that we had a different phase angle, but all of these, the graph is the same, so no matter what form we're asked to express it in, we will be able to obtain the same graph from that. So just pop back to example 2 here and give you a minute to copy that down.